please.
So thanks for inviting me. And I guess the question I'm going to be talking about today is the following. So let X be a two-dimensional simplicial complex. And we're interested in the following variant of the Turán problem. So what is this extremal number, which I call x-hom for homeomorph. And this is going to be the maximum number of two simplices, or triangles, in an n-vertex simplicial complex such that no subcomplex of y is homeomorphic to x. So this is pretty similar to the standard Turán question, except instead of isomorphic as subgraphs, we're interested in, I guess, the topological property.
What did you write over there? Is that notation x-hom to
X sub hom of n comma x.
Oh, n comma
Sorry.
x, okay.
Yeah, so this is the same, I guess the same as the normal extremal number notation. And I also want to remark that this is the same thing as if I replace the simplicial complex by a three-uniform hypergraph. And these things by three edges. This really is a hypergraph Turán problem where the forbidden set is all, I guess the forbidden family is all triangulations of the space X.
You mean y has dimension 2 or so?
Y has dimension 2.
Okay.
So I guess three edges and two simplices are both triangles. Yeah. So think of X as being the sphere or the torus or the real projective plane are the examples I'm going to talk about the most today. So I think it's worth mentioning if we go down a dimension, then this becomes a question about graphs. How many edges can you have in an ordinary graph so that you don't have a subdivision of your forbidden one-dimensional simplicial complex? And there's a theorem due to Motter that if G has no subdivision of KT, then the number of edges in G is at most, some constant depending on T times n, where n is the number of vertices. And then for the lower bound, we can take, I don't know, G to be, if G is a tree, then obviously G has no subdivision of KT. So that tells us that n minus 1 on the left so this tells us that it's linear in n. So I guess dimension 2 is the first interesting dimension. And I guess this has been studied first in the case of surfaces, so sphere, any whole torus, or non-orientable surfaces, and then has also been studied for other simplicial complexes. So some historical overview. Is that visible? For the sphere, It was done in the 70s by Brown. And I'll talk a little bit about this upper bound in a sec. Then for arbitrary surfaces, we got the matching lower bound. So here the constant in the big O might depend, or definitely depends on the space X. And this is, I think, due to linear. Question mark, because it's very, like, I found this result claimed, but the only proof I found was attributed to, I'll write these names out in a sec, in 2021, Lipovsky, Plansky, Tone, and Sakharov. And this proof uses the method of alterations. So the rough proof sketch is you take the random graph G and P, so each triple exists with probability P, where P is about 1/√n, and you count the number of copies of X. So for each possible triangulation of X, you count the number of copies that show up, and you show that this is less than the expected number of triangles. And this requires a result on the number of ways to triangulate a surface with a specific number of vertices. I don't want to do the computation out explicitly, but this is the idea of it. And then matching upper bounds, Lipovsky, Plansky, Tone, and Sakharov. So they proved two things. They proved that for the torus, sorry, I think I...
The above you need some...
Yeah, I think I switched the big O's and yes, sorry, this should be a big omega, I think. Yeah, sorry. And then they also showed that if two spaces have if two spaces both get n to the 5 halves, then their connected sum also gets n to the 5 halves. With possibly a different constant here. And when I say connected sum, I mean I take my first space and my second space, and then I cut out a small disk in each one, and then I glue them together. So the connected sum of these two is a 2-hole torus. And when this was in 2022. And then lastly, a result of mine last year, match this bound for RP2. So this is the real projective plane. So this, I guess, gets the bound for all surfaces. So just a classification theorem of surfaces. All surfaces are either the sphere, a connected sum of toruses, or a connected sum of handle bodies. So this, I guess, combining all of the results out here, this tells us that we know the bound for all surfaces. And then lastly, I want to talk a little bit about what we know for spaces that aren't surfaces. So is this one? For so first, for other two-dimensional simplicial complexes, for so Kivash, Long, Narayanan, Scott showed that there's actually a universal exponent that, so a bound like this for any arbitrary space X. So for any two-dimensional simplicial complex X, we have that the exponent is at most 3 minus 1/5. So that's a little bit worse than 5 halves. And a result of mine that's not yet on the archive, but hopefully will be soon, is the same thing with 3 minus 1/3. And there's some interesting things here because I think the problem of getting this exponent lower actually mostly turns into a question about bipartite Turán problems. Essentially, it reduces to finding the Turán exponent for an appropriate bipartite graph. And I'll talk a little bit more about that later.
Does the lower bound apply?
So I'm not, so the lower bound doesn't apply for every X. A sort of stupid example is a disk. I believe the lower bound applies for any reasonable space X.
Not like a disk.
Yeah, but I think mostly the reason I haven't checked it is because this argument that used alterations goes by, I guess when you're counting the expected number of copies of each triangulation, it cites a result on the number of triangulations on each number of edges, and my topology isn't strong enough to figure out whether that holds for things that aren't surfaces. So my guess is for any reasonable space, the lower bound probably holds, but I haven't checked it.
But your upper bound does hold for disks in particular?
Yeah.
Okay.
I mean, for disks, the
Don't you just need one triangle?
yes, yeah.
Yeah.
For disks, the
It's
XCOM is just
yeah,
one.
of course.
Yeah. So if you have a sphere, then you have a disk. Or well, if you have a triangle, you have a disk.
Yeah.
Yeah. But yeah, certainly any space that contains any surface as a subcomplex is going to have that lower bound applying to it. And then, oh yeah, one more thing I want to mention is in dimension D, we also know that there's a universal exponent. So this is due to Long, Mara, and Yap. So for any r-dimensional x, so there's some universal exponent r plus 1 minus epsilon r. That's the epsilon r depends only on r. It doesn't depend on the space x. So it's an analog of this result, except the dependency of epsilon r on r is a lot worse. And this also relies on looking at a degenerate Turán problem for r plus 1 uniform hypergraphs. So I'd like to talk a little bit, if there aren't any questions about anything here, I'd like to talk a little bit about the proof ideas for a couple of these things. So how we do the torus, well actually sphere, torus, the real projective plane, and also how we build an arbitrary two-dimensional sub-simplicial complex. So this is the part of the talk where I get to draw pretty pictures. I guess I'll start by telling you how we find a sphere. So to find a sphere, we're going to actually find something much more specific. We're going to find something called a double pyramid. So what this is you have a cycle of some length, and then we have two vertices, one at the top and one at the bottom. And we take every triangle with the top vertex and one of the middle edges, and every triangle with the bottom vertex and one of the middle edges. So we get a pyramid on the top, and we get a pyramid on the bottom. And the idea is if we can find one of these things, it's homeomorphic to the sphere. So the way we find these things, so we look at what's called the link graph. So we pick a vertex u in our simplicial complex y, and we look at the edges of the link graph correspond to triangles containing u. So it has an edge VW. For each triangle UVW in Y. And I'm going to denote this LFU. So in the example of the double pyramid, if the top vertex is U and the bottom vertex is V, then finding a double pyramid is the same thing as finding a cycle within LU intersect LV. So each of these red edges is going to be an edge of the link of U and also of the link of V. So the question becomes, can we find one of these intersections that has a cycle? So suppose that Y has at least Cn to the 5/2 triangles. Then the average link has at least three C n to the 3/2 triangles, just because each triangle has 3 vertices. And then if things looked random, then the average intersection L of U intersect L of E. So in the random case, we'd have, sorry, these should be edges. Yeah, my bad. In the average case, if everything looked random, we'd have at least 9 c squared n edges in the average intersection of 2 links. And so in fact, you can show that this thing is at least what you'd expect in the random case by Cauchy-Schwarz. So if we pick C large enough, then we can find U and V that are distinct so that this thing is at least n. But if this thing has at least n edges, then it's got a cycle and then it's done. So that's how we prove it for the sphere. For other topological spaces, it becomes more complicated. So the general strategy is to find some sort of one-dimensional skeleton graph and glue disks to it. So what do I mean by this? An example in the torus case is we find something that looks like this. So we find a cycle that is just formed of a bunch of triangles, and that wraps around. So it's sort of like a strip. And then what we do is we glue disks to this thing. So we glue disks this way, and we glue disks this way. So as you can see, I've sort of drawn, so I guess maybe one way to picture this is I glue a disk to this set of 4 edges, and then I glue another disk to this set of 4 edges, and another disk to this set of 4 edges. And if I keep doing this, eventually I get a strip. And then similarly, I do the same thing going the other direction to get a second strip. So if you sort of take the yellow strip and the red strip, and you notice that they're glued together, this thing looks a little bit like a cylinder. So you get a cylinder that looks like this. But I've told you that this structure that we're looking for wraps around. So the cylinder that I've given you also wraps around. And you need to check that we get a torus and not a Klein model. Because if I take a cylinder and glue its ends to each other, you can get either a torus or a Klein model. But sort of the heart of this argument is 2 things. First, we need to find the triangle cycle that I drew above. And then the second thing is, and this needs to be of bounded size. And the second thing, which is what I'm going to talk a little bit more about, is how are we sure that we can glue disks to each of these C4s? And in particular, non-intersecting. So for RP2, the strategy is a little bit simpler. So I'm going to so first I'm just going to draw RP2. So RP2 is you take a disk and then you glue this half of the disk to that half of the disk typically. And I'm going to draw one more arrow in the middle, just for kicks. And if we look at what the two lines A and B look like in this picture, they form a subspace that looks like this. Because actually this point and that point are the same, and so each of them is just a loop. And we can get the real projective plane from this subspace by gluing in two disks. So the first disk is going to correspond to this region out here. So that disk is going to be glued to A, followed by B. And then the second disk on the right-hand side is going to be formed by gluing a disk to the loop B. So we follow B. And then we follow the reverse of A. So our proof strategy is going to be to find two cycles that look like this, and then somehow find disks whose boundaries look like this, and like that, and glue them in. So the first naive idea is let's do a double pyramid-like thing. Find U and V, and we'll find this cycle. Let's call this W, A1, A2, AK. So we'll find two cycles. Let's call this B1, B2, all the way to BL. So we'll find something like this between the two lines. Because out there we just found one cycle and glued something to its top and glued something to its bottom. So maybe we can do the same thing here. And then we'll let our first disk be. So we follow, I'll draw it up the right. So each of these triangles exists because we're because these two cycles are in the link. So I'm going to find a bunch of triangles centered at U, and I'm going to just say, let's follow my two cycles along this loop, and let me build a disk this way. And unfortunately, this thing I've drawn isn't a disk, and the reason it's not a disk is because this one simplex shows up twice. So it's not quite a disk, it's more of a disk with then like a line glued together. So how do we fix this? Well, let's just take this C4 and let's replace it with a different C4 that doesn't have the blue one simplex. And if we do that, then all of a sudden we really do have a disk that has the right boundary. So once again, sort of the thing that we really need is we need to be able to find a disk that we can glue to this C4 that avoids all of the vertices in our cycle. And then similarly, we'll get, so that's how we got the disk with this boundary. To get the disk with this boundary, we do the same thing, but centered around V instead of around U. And so then the last type of space I want to talk about is the general two-dimensional simplicial complex. So to handle an arbitrary simplicial complex in 2 dimensions, we just need to handle the complete graph so we have T vertices and we have every triple of them. And the way we handle this is we build a graph so the vertex set is going to have size t choose 1 plus t choose 2 plus t choose 3. And we're going to connect vertices vi to vij and vi to vijk. So part of this graph might look like v1, v2, v3, v1, 2, v2, 3, v1, 3, and then the last thing we're going to do is once we find this skeleton graph that has roughly t choose 3 vertices, we're going to glue a disk to each C4 that looks like this. So we're going to glue a disk to each C4 of the form B sub I, B sub ij, B sub j, B sub ijk. So once again, if we can find a copy of this graph I've described, where each of the C4s is something we can glue disks to, and the disks have to be non-intersecting, that's pretty important, then we're done. So the question really becomes, how do we sort of show that many C4s are coverable by many disks. And we need this to be in some sort of robust manner so that I can guarantee that like the yellow disk doesn't intersect with the blue disk, and so on. So the way this works is by probabilistic techniques. So I guess the rest of the talk is mostly going to be probabilistic. So I'm going to use the notation U subset V with this P to say U is sort of randomly sampling each vertex with independent probability P. And I say a cycle C of Y is P epsilon disk coverable if there are many disks that have that boundary. If the probability over all subsets of U, or subsets of V chosen with probability P, the probability there's a disk whose boundary is the cycle that we're interested in and whose interior, using the little circle for interior, is taken entirely within U. So what this is telling us is that for almost all choices of U, we can find a disk that only goes through the vertices of C and vertices of U. So in the example out here, if each of the C4s we care about is, so there's 3 T choose 3 C4s total. So let's just divide the vertex set into 3 T choose 3 different parts. And then let's take epsilon equal to then what we can do is we can randomly partition V into 3 T choose 3 parts. And by a union bound, the probability that there are non-intersecting disks as desired is going to be at least 1 minus 3 to choose 3 times epsilon. And I picked epsilon to be so that this thing is greater than 0. So if we can find an embedding of gamma T where each C4 has the disk coverability property, then we're done. So the question becomes, how do we find disk coverable C4s? So one more definition. We say an edge xy So let G be an ordinary graph. And we say an edge is P epsilon admissible. If similar condition. So once again, we pick U to be a subset of V, take them with probability P. And we ask, is there a cycle from X to Y where all other vertices are taken within U? And this similarly is saying that there are cycles from X to Y in some robust manner. And the reason we care about this is because observe that if an edge xy is P epsilon admissible in some intersection, LU intersect LV, then that's the same thing as saying that this cycle is P epsilon discoverable. So the reason this is true is because if we can draw a double pyramid as before. So if there's a cycle from X to Y within U, then I can turn that into a double pyramid. And this double pyramid is a sphere that, if we take out the two triangles corresponding to xy, becomes a disk. So we get something that looks like X Y, where all the interior vertices are in U. And then this thing is a disk which has the properties that we want. So the problem of, I guess, counting discoverable cycles can be boiled down to counting admissible edges in the intersection of a link graph. So let's talk a little bit about how we bound such things. Most. So we can actually bound the number of bad edges in terms of the number of vertices of a graph, and totally independently of the number of edges in that graph. And the proof of this is kind of nice. So let big N be the number of bad edges. So the number of edges that are not p epsilon immiscible. And choose U as a subset of V. So we look at the bad events so this is the event that both X and Y are in U, but there's no cycle containing XY. In U. And let B equal the number of bad events. So the first observation is that if we look at all of the edges for which the bad event hold, those edges have to form an acyclic subgraph of the induced subgraph on U. And the reason for that is because each edge for which this thing holds is not in a cycle in the induced subgraph on U. So that tells us that this thing is a tree, so the size of B is B is less than the size of U. But the other thing is that the expected number of bad edges, well, each edge that isn't admissible is going to have this thing hold with probability at least P. And this probability is going to be at least epsilon P squared for each of the bad edges. So we have that this thing is at least epsilon P squared N, but also it's at most the expectation of U, which is Pn. And combining these two bounds, we get that Pn is at least epsilon P squared big N, which gives us the bound that we want. So using this lemma, one can bound the number of 4 cycles of this form that are not discoverable. And that's ultimately how they were able to get a bound on the torus. So for RP2, I needed something a little bit stronger. So oh, actually, I should first say, if X and Y are disconnected, then this definition is the same thing, except instead of cycle, we get a path. If XY is not an edge. So we can define it for any two vertices, X and Y, that aren't necessarily connected in G, but counting the number of vertices that are robustly connected in some way really requires that we know that the vertices are connected at least a little bit to avoid them being like disconnected components, for example. So let A be the set of paths of length 2. with x and z not admissible in some graph G. Then, so unfortunately, it's impossible to just bound the size of A, but you can say that the sum so counting each of these paths with this strange weighting factor is at most 3n over p squared epsilon. So this is kind of a weird result. And the reason we need this sort of weighting factor at all is because consider the example a clique on square root of n vertices and then a bunch of leaves, n minus root n leaves. So in this example, almost all the paths are not admissible because most paths of length 2 are between 2 leaves. And just intuitively, any 2 vertices here are not robustly connected. If this vertex isn't in U, then that's game over. So most paths of length 2 are not p epsilon admissible for any reasonable choice of parameters. So this tells us that it's impossible to get some result like this without any sort of weighting factor here. And it turns out that this weighting factor is actually useful. So one thing we can observe is that so the same observation I made up here, if we have something like this, so if we have 4 triangles, and W and W prime are well connected in the intersection of links, then by the same reasoning as before, the C4 VW V prime VW prime is going to be p epsilon discoverable. And we can make another observation, which is this 1 over degree y term. Well, if we look at the degree of u in the graph L of v intersect L of v prime, this is the same thing as the number of vertices W prime, or W prime prime that look like this. And if we look at this picture and sort of turn it 90 degrees, we see this is the same thing as the codegree of v and v prime in the graph L of u. So using this observation, we can actually get a pretty reasonable bound on the we can get a pretty reasonable bound on the number of discoverable C4s in some specific link. So by an averaging argument, if y has at least n to the 8/3 triangles, but really you could bring this thing down if you wanted to. This is just the form that one would need for the, I think, for this bound, getting 3 to n to the 8/3 here. If y has at least this many triangles, then there exists a vertex u such that the link graph has close to the average number of triangles. Or this is roughly the average number of edges, but it might be divided by 2 or something. And if we sum over all pairs of vertices in the link, the number of C4s from between B and B prime that are not P epsilon admissible over the over their codegree in the link is at most some bound that I don't want to write out. But the point is that this follows almost immediately from the lemma I wrote down here, because of this observation that this 1 over the degree term can be rewritten as the codegree of B and B prime. And the other nice thing about this lemma is that it tells us, so if we look at this term, the number of these C4s that are not P epsilon admissible, this term we can sort of think of as being, so it's at most the codegree squared. So this is sort of something stronger than telling us that at most a small fraction of C4s are bad, because it also tells us that if V and B prime are particularly well connected, then an even smaller fraction of C4s is bad. And using these sorts of bounds, we can use dependent random choice to embed this graph gamma t on the right in L of u, such that each of the 3 t choose 3 C4s is discoverable with the appropriate parameters. And that finishes the proof that the extremal number of this thing is at most n to the 3 minus 1/3. So I guess one thing I want to mention is using dependent random choice, this is also how you get the Turán number of this thing. So this is the standard extremal number, not the homeomorph one. So with dependent random choice, we can get this exponent. And my question is, can we do better for the extremal number of this graph? Because if I can get any proof technique, I think, that gets a smaller exponent here, can hopefully be extended to showing that, well, if this link has at least that many edges, then not only can we find a copy of gamma t, we can find a copy of gamma t where each of the C4s is discoverable. So I guess one question. I guess, can we improve? Because that's sort of the limitation for why this proof, I guess, stops out at 3 minus 1/3. Or can we use a different bipartite skeleton graph, which has a better Turán exponent than 2 minus 1/3. So yeah, that's what I had.
Any questions? I have 2 questions. So the Mother's theorem allows us to get a corollary that are interesting to me. Like the one corollary is that if you don't have a KT topological minor, then you can so the chromatic number is like basically bounded by a function of t. And the other is like not only you bound the number of edges, but you can also bound the number of clicks by a linear function of the number of vertices, just by induction.
I
Just
see.
delete one from smallest degree and you keep doing it. So I want to know whether something like that could be possible. For instance, now you know the number of this two-simplex is bounded. Can we say that number of complete uniform, I forgot, or whatever. So analog of click is also bounded.
So the
by
question is like bound the number of k like complete ks if you're free of homeomorphs of kt.
Right, something like that. So that's one question, and the other question, next question, like in terms of coloring, I mean, I was during the talk, I was thinking, what could be the analog? Maybe you want to color the edges. I mean, what I mean is once that line, you want to color the edges so that the triangle, so no triangle is monochromatic, something like that. I mean, because in a graph case, you want to color vertices that no edge get monochromatic.
So Mado's theorem tells you that.
Yeah,
what is this chromatic corollary?
You want to color the vertices of the graph so that number of colors bounded by a constant, I mean, some function of t.
And you can do that if there's no
And
subdivision of kt.
yeah, if you don't have a subdivision of kt, then it's like. But the difficulty here is, it would be nice if you can find the bound in terms of the number of edges, right? Right. By edge I mean, how should I call it? Like one cell?
Yeah.
Yeah. So currently it's about number of vertices, but can you say like find an upper bound in terms of number of one cells? That could be useful if you want to do the induction, but I don't know whether this is meaningful.
I have no idea. Yeah, I haven't thought about that at all. That is an interesting question.
Okay. I think I had some questions, but anyway. Other questions? Oh, if not, let's thank the speaker.